Good morning, Professor.
Good morning. Thank you. Good morning. Good morning, Catherine. Good morning, Daniel. Good. Thank you. Good, hello, Ashley. Good morning, Molly. Good morning, Nikaya. Very well, thank you, Ashley. How are you? Well, okay, good. Thank you. Good morning, Alyssa. Good morning. No. Good morning, Camilla. Good. Good morning, Michelle. Good morning, Tarina. Awesome. Okay, awesome. I love it. Oh, did I say Ashley? Sorry. Hello, Ashley. Oh, I did. Oh, good. Thank you. Right. Okay, got it. And I owe Daniel a G for the end of good morning. Good morning. Good morning, Zitlali. Awesome. Awesome. Okay. Okay. Awesome. Awesome. Okay. Okay. Right. Let me. Okay. I still don't have them, by the way. I feel terrible. I'm not even going to dwell on it. I don't have them yet. It's nothing you did. It's what I didn't do. Hopefully you're not going to have to wait till Monday. I'm just, when I get them done, I'm just going to send them to you guys, but I'm sorry. I don't have them yet. That's all I have to say about that. I'm a terrible person. Well, yeah, anyway, I do apologize, but I don't have them yet. That's all I have to say about that. Hold on. Okay. But we're going to go on with the, but for whatever it's worth, oh wait, there's something else here, I think. Okay. Yes. We're going to get straight to material today, back to the material. Um, Also, now I know a lot of other things have come in the last couple of days. Thank you, like game assignments and stuff. I have to turn them back to you. I haven't yet. Um, One little thing though, or just one other logistical update before we get back to material, but obviously you can stop me at any time with questions or please do. And good morning, Yasmin. Thank you. Awesome. Good morning. Oh, and my dude is missing an eye, it looks like. Oop, uh, um, yes, for whatever it's worth, I also had a very long talk, a very good talk last night with Professor Wu, actually a 4-hour talk with Professor Wu. So we caught up on a lot of stuff and definitely, and we shared a lot of notes about you guys and how you're doing and what's going on in lab. So, and there's not, so I just want to say like, I'm impressed with what you're doing in lab. I know where you are. He knows where you are here. He knows you haven't gotten the exams back yet. He understands that. I mean, anyway, but just so that you know, we're trading notes and trying to keep all this coordinated. And he says hello and all that. Okay. Oh, wait, there's more people here. Okay, okay. Um, okay. Um, um, okay, 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 okay. Good morning, Melissa. Thank you. Good morning. Awesome. Oh, and there's more people. Sorry, sorry, sorry. Hold on, hold on. Thank you. A funny story that really quick that he reminded me of that happened a number of years ago. Again, speaking of exams, a number of years ago in Physics 204, during the summer one year, this is obviously before COVID, so we were in the building and blah, 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 but it was a summer. We had a final exam coming up in Physics 204. Again, this is a story for anybody who just joined. This is just a story that I was reminded of. I mean, it's totally a true story, but has nothing, no moral, no lesson, just a way to start the day. Man, I guess there's a moral, but anyway. And good morning, Melissa, if I didn't say, sorry. So years ago, summer, Physics 204, final exam coming up, and we decided to make it a take-home exam for a number of reasons. It was one of the first times we started instituting take-home exams. It was a bit of an experiment. It was partly because we needed the lecture time to do more material, something. And so just like we do now, even though it wasn't COVID and things were not online or anything like that, it was like a normal class, but we still said, okay, the final exam is going to be take home. And just like now, we said, okay, but our philosophy on cheating and all that is what it is. And, we don't, I mean, it's like totally stupid to put people in a temptation scenario and put people in a position where you're only going to get an advantage if you cheat. And then the other people who didn't cheat get a disadvantage. Like it's all stupid in my opinion. So again, this is years ago, like 2015 or something. And so I said to everybody, the same thing I say now, I say, okay, Y'all can work together. You can do whatever. You can go on the web. You can do, just like with you guys, you can do whatever you want. You can totally work together. But at the end, you know, your work is yours. You put your name to it. You get a grade on it. Even if you collaborate with everybody else, by the time you write out your exam, you write your exam. Again, for anybody who's just tuning in now, it's a story. Oh, more people are coming in. Sorry. This is just a story, a true story of something that happened. It is not any reflect, and it's just on my mind because I was reminiscing last night. So it's not reflective of anything you guys did or anything like that. But it was in the early stages of our experiments with. Good morning, thank you. Good morning, Jennifer. Good to see you. It was. I like that, and anyway. Thank you. So we said to them, you can work together, and of course we were secretly hoping that they would, because we think that that really actually helps when you work together. And again, it's something that I think is a loss during COVID, that you don't get to work together quite in the same way and all that stuff. But so we said that to them, you can all work together, you can do whatever, but in the end, your exam is your exam and you get your grade, right? And again, for anybody who just joined, I don't have the exams back. I'm sorry. I really am sorry about that. I'm just going to keep saying it just so there's no confusion. So everything I'm saying right now is not about your exams. I don't have them back yet. It is my bad. I apologize. But anyway, this is just a story. Maybe this will lighten anxiety too. I don't know. It might increase anxiety. Oh my God, another person's going to talk about anxiety. Another person's coming. Sorry. Also, maybe remind me before the final exam, I should tell you all. I mean, believe me, I'm a very anxious guy, if you can't tell. I know some of you people have anxiety. I totally can relate. I certainly had anxiety as a student. And remind me before the final exam, or maybe after I give these back, I do have some scientific perspectives on anxiety that might be slightly helpful. They were helpful to me when they were given to me a long time ago. But anyway, we give this whole, good morning, thank you. Yes, good morning, I think we said that. So we give them this take-home exam. They have like a week to do it. They're allowed to get together, all of that. We expect them to get together in some fashion. Well, they really all do get together. Good morning, Aja. Thank you. Awesome. Good morning. Good morning. They do. So this class, this 204 class during the summer of like 2017 or something like that, it turns out, now I don't find this out until later, but it turns out the entire group, and it was like 48 of them. I mean, this was, in a lecture hall and everything back then. So it was like, there's like 48 people in this class. It turns out that for the most part, all of them really got together. Like they made a party or something, and they physically actually really, maybe it wasn't 48, but like this huge group of them all get together, and they literally did the whole exam together, or, and they made assignments to each other. Like they made a thing out of it that they were going to crack this exam as a group. And partly, I think they were going to show me like, okay, dude, sucker, like you're letting us work together. We're really going to work together. We're going to make sure we got this thing solid, and we all are just going to contribute a part so we don't have to work as hard or whatever. So they all work together and they do the whole thing like literally together. And again, I don't know this is happening while it's happening. But then it sort of does become very evident when I look through the exams. There's like a huge similarity among all of them. But, I had said that this was okay, is okay. But okay, the one thing is that when I say, oh my God, more people are coming. Sorry. The one thing was that they really did all get together and really do it. Kind of, they made like one pretty much identical exam, which was not the right thing to do. Like they didn't like vary it. After they went back to their private Idahos, they just kind of like wrote it all together. And that's kind of suspicious in itself, or was kind of sketchy. But the truly sketchy thing was that they all did this, except there was one kid that they did not invite, that they just didn't invite or wasn't part of it at all. And partly maybe because at the time his English was not super developed, or it didn't seem that way, or he had a thick accent or whatever. So, and he wasn't like in the midst of the social stuff. So they left out this one kid. Again, I didn't know this at the time, but they did. So they all do the exam together, except for this one kid. I shouldn't say kid, I'm sorry, this one student. They leave him out. They all do it together. I get all the exams. All of them look almost identical, but I'm still grading them and everything, except they're not that good. It turns out the ones that all looked identical, they all end up getting like around a very similar grade, and the similar grade was like a 77. The one kid who wasn't invited, the one student who was not invited to participate or didn't even know about it, and was left out in the dust to do it all by himself, he got a 98. Now, what's the point of the story? And I wasn't punishing that. Like, I didn't know this happened. I just graded these, but they were all very similar, but they weren't that great because the whole group had sort of sunk to the, how the chain is as strong as its weakest link or whatever. They kind of just like sunk to a certain level and just accepted all their stuff is correct. But like, it was like mob mentality and they all got like a 77, except this one guy who wasn't invited and got a 98. And that would kind of be a punchline in itself, except maybe not worth telling the whole story, except for the name of that one student. Maybe you can guess. And like, if this were a truly cheesy story, like on TV, that one student was me. Well, no, because I was the professor. The student wasn't me. But I don't know if you can guess who the one student was, but I'll just tell you his name. You now know him as Professor Kim, as Professor Wu. That was Professor Wu. He was a student at the time. And that was one of the things that happened along the way to him, to me totally wanting to hire him and give him a job and everything. And now, now he's Professor Wu. But that's how his career began, being the one kid who was left out and got a 98 while everybody else got a 77. Just saying. The guy, his brain is, his brain is bigger than a planet. I don't know if you've noticed that or not. And still, occasionally he talks with an accent. I know that it's occasionally hard to understand him, but let me tell you something. I spent a lot of time with the guy and 4 hours with him on the phone last night, and that's a drop in the bucket. And I'll tell you what, in his third language, he thinks more deeply than I do in my native language, and that is clear to me. Any hoodles. That's perfect. Also, you should see how he paints, but that's a whole other thing. Paints like paintings, like, oh my God. But okay. So that's just my little bit on Professor Wu, again, because he's kind of on my mind because I got to catch up with him for a long time last night, and that's good. And that's good for the class. It just helps keep us connected. Okay. But it also goes to show you, like, you should work together and stuff, but you should always then at the end, do your own checking on what happened. Okay, back to physics. Oh, my internet connection is unstable. So is my personality. What's new? Hold on. Oh, it is unstable. Okay, sorry. Okay. So here's where we're going to do something that is also going to dovetail with what you're going to see specifically in lab with him, like shortly. In a rare moment, I'm going to try to do it a little bit first instead of afterwards. What this is all going to be, this is all going to be about. What we're about to do is a expansion analysis explanation of how to use Newton's second law in order to solve problems and do physics. I spent a long time yesterday talking about the first law and the third law. They're written in English. What they're really trying to do together, again, to remind you, like, the first law is telling you what's happening when no forces act on an object. The third law is telling you what a force really is. And just to remind you again, a force is a symmetric interaction between two particular objects. I would write that down again, but I don't want to get bogged down. I want to get straight to Newton's second law. I feel like we wrote it down yesterday, but let me just say it again. Like Newton's third law says, if I push you, you push me back with the same magnitude in opposite directions, right? That's what I was trying to explain yesterday. We're going to see that again today in English. So it's the action-reaction force law, but what I'm really trying to say about Newton's third law, or what I was really trying to say yesterday, is that don't just say, oh, for every action, there's an equal and opposite reaction. That's way too vague. And it leads to a misunderstanding that a lot of people have. A lot of people end up thinking that it means if some sort of force pushes an object to the left, then there must be some other kind of force pulling or pushing the object to the right. Like, that's very easy to think that's what it means. That is not what it means. That could not be right. It could never be a law. It is not a law that if something is pushed to the left, it necessarily must also be pushed or pulled to the right. If that were a law, nothing would ever accelerate. The law is, if one thing pushes another to the left, then the other must push the one to the right. It's always trying to tell. So the Newton's third law is trying to say, whenever you want to picture a force, you got to picture two objects interacting with each other. That is what a force is about, is one object interacting with another object. And interacting ultimately means pushing or pulling. And we say, according to Newton's third law, that all interactions, all forces between objects are symmetric interactions. So if I push you, if I push the wall necessarily pushes me back. By the way, that's why my hand hurts, right? Or by the way, that's why I bounce back when I push the wall, right? Et cetera, et cetera. But furthermore, so if I push the wall, it pushes me back. If the earth pulls me down, I pull the earth up. That is a law. And furthermore, if the earth, and this is what we're going to start analyzing today, if the earth pulls me down with a certain number of units of force with a certain strength, then I pull the earth back up with the same strength. Please note, that's the sort of surprising maybe part of the law. And it almost sounds wrong when you really think about it, or if you think of certain cases. We're going to see today how it's not wrong, but just as a quick overview again, why it's right or how you can believe that it's right. Like never forget about the second law. Put another way, if like a little like bicycle hits a huge Mack truck, or a Mack truck hits a bicycle, which is the same thing, we're saying. And doesn't that sound like Galileo's principle again? Yes, it does. It's like this is like the seventh form of Galileo's principle of relativity. Like you can't say I push you without automatically understanding that you're pushing me. And it doesn't matter, no one's going first, no one's going second, doesn't matter who's thinking about it or not, doesn't matter if they're inanimate objects. Anytime something pushes something else, then the other thing pushes the first thing, and just as hard. So, and I'm getting all bogged down here, but so if a bicycle hits a Mack truck, then the Mack truck hits the bicycle back at the same time, just as hard. And it's not even like a cause effect. It really isn't action. You can call one the action and the other the reaction, or you can call the other the action and the first. There's no actual distinction. It's happening at the same time. Just like I married my wife on the same day she married me. It was not, and that's not a coincidence, and that's not a surprise. It's just the nature of it, right? But furthermore, I'm saying if a bicycle hits a Mack truck, the Mack truck will hit the bicycle with the exact same strength. Now, it might not look that way to most people. You might think, well, wait a second. A Mack truck hits a bicycle? The Mack truck is like basically going to keep going, and the bicycle is going to like boing and like go flying off. So what do you mean they're obviously not hitting each other with the same strength, one might think. But here's what I'm saying, and this is what we're going to get into today is, oh, yes, they are hitting each other with the same strength, with the same force, but what you're seeing with your eyes, what you're noticing, what you can measure and observe and all that is the acceleration that results. When you see the bicycle go flying and you see the Mack truck barely even slow down, but slow down a little bit nonetheless, what you're seeing is acceleration. And for sure, the bicycle will accelerate a lot more than the Mack truck because F net equals MA, because of the second law, which is what we really want to start analyzing today, which is where the really math sits and everything. Like F will be F, the same. A Mack truck, a bicycle, one will F, like the bike F's the truck F's the bike with the same F, but F equals MA. So because the bicycle has a much smaller mass, then a given M will result. Because the bicycle has a much smaller mass, it will accelerate, like small m times big A will make the same F as big M times small a. Like that's what we're about to see. But what you see is that objects will accelerate differently in response to the same force, because that's what Newton's second law says. The less heavy you are, the more you will accelerate in response to a given force. But the force by Newton's third law will be the same. Okay, so what we're going to, I don't know if that helps or not. So the first and the third law are trying to give you a physical or a visual picture of what we really mean by forces. What happens when they're not there, when they're not acting on an object, what happens when they are acting on an object, or what they are when they're acting on. Now, the second law is going to specifically mathematically predict for us exactly what the results will be in terms of acceleration. And the way we analyze this law is through this thing called free body diagrams. So here so again, stop me anytime. and I'm going to take a breath in a second, but here we go. So oh, wait, oh, sorry. The second law is not a form of, sorry. Sorry. Okay. Okay, so we're going to analyze F net equals MA. We're going to show you how to use it in terms of free body diagrams. First thing, so F net equals F. So the big symbol, the sigma symbol means you add. So the law is not F equals MA. The law is not a force equals an acceleration. It's if you add up all the forces acting on all object, on all mass, M, then you will thereby find out the acceleration of that object. But specifically, this is a vector equation. I put the arrow symbols above F and above A saying acceleration. A good old acceleration is a vector. Force is a vector. In other words, it acts simultaneously but independently on all axes of space, like we were saying a couple weeks ago or a week ago, right? In other words, actually another way to put this before I go any further, I'll write this. No, I'll write that in a second. But to say that F net equals MA as a vector equation really means that F net equals MA on the x-axis, and at the same time, but independently, F net equals MA on the y-axis and on the z-axis, if there is one. So truthfully, F net equals MA is really secretly three equations, one for each dimension, happening simultaneously yet independently, like all the time. And furthermore, we're taking into account direction. So when I say add up all the forces on an object, I mean add up all the forces acting on that object in a particular axis, and definitely do take into account directions. Like anything that's going left is different from anything that's going right. One of those directions will get a negative sign and the other will get a positive sign. Okay, that's like the first just like warning. By acceleration, which is still a vector, we mean what we always meant. We mean, well, average acceleration meant to us in the first exam, like change in velocity per time. But here we're talking about instantaneous acceleration, acceleration at a point. So that really means derivative of velocity with respect to time, which is to say derivative of position with respect to time. Acceleration, instantaneous acceleration, is a vector that measures the instantaneous which measures the second derivative of position with respect to time, right? That so, and it's just to remind you or whatever. I don't know why that's doing that. Sorry, just to remind you, it's measured in units of meters per second squared. Like that's all from like the first exam. Okay, and you might know this is why we spend so much time on acceleration, because it turns out this is the thing that we can predict about objects, because this is what forces produce in objects. Okay, so that's acceleration, just like a reminder. Now, well, I'm just sort of reading right to left here. By mass, I know you've heard this, some version of this a million times in other science classes, but we have to get it straight right now. M stands for mass. That is not the same thing as weight. It's not the same thing as volume. There's different definitions of mass, but here, it's how big an object is, sure, but specifically, what we're really talking about here is something that some people will very specifically call inertial mass, or even some people will just call inertia. And what we mean by it here, well, really what we mean by it ultimately is defined by this law. What we mean by it is resistance to changes in motion. So the more massive you are, the more massive you are, the less easily you change your velocity. I mean, that's what the second law is saying. So if I have twice as much mass as you, that means it would require twice as much force to accelerate me, to either speed me up or slow me down or turn me as it would you. That's what mass means. We'll see that more in a second, but more specifically, just to be clear, the units of mass are, as you know, are kilograms. Okay, and okay, the mass of something, and I know you know this from chemistry and stuff, but just to put it in a physics context, when we talk about the mass of something, maybe for the first time in this course, we now are talking about what I would call a property of a single object. Remember, I keep trying to emphasize, because it's like a really big distinction in physics, I keep trying to emphasize like velocity is not something that you have. It's something that you have in comparison to something else. Same thing with force. Force is not something that an object has. It's something that it does to another object. Forces and velocities are relations. I know I keep saying, but it's hugely important. Forces and velocities are different types of relations between pairs of objects. Mass is a property of an object. Like every time I say the velocity is not a property of an object, in a way I'm contrasting it with mass. Mass is something that an object has. Like my cup of coffee has a certain number of kilograms of mass. And it's so, I'm not saying I can't change that. I'm not saying I can't shrink the coffee, or like melt the, or, make my coffee cup bigger or something. But until I do something, I'm saying my coffee cup has a mass of 3 kilograms. I don't need, that doesn't mean it has 3 kilograms more than my calculator. It just has 3 kilograms. And it's so true that like, even if I bring my cup to the moon, my coffee cup to the moon, it's still going to have a mass of 3 kilograms, which means as hard as it would be to push here on Earth, like if I have to, if the coffee cup is really massive, and so for me to push it across the table, I have to like push it this hard, that's going to be exactly as true on the moon. Now, pushing it up might be a different matter because that gets into weight, but the mass of the cup is the mass of the cup, even no matter where it is, okay? And it's measured in kilograms. So acceleration is measured in meters per second squared, like you know from the whole first chapter. Mass is now measured in kilograms. And generally, whenever we talk about a mass from here on in, we're going to talk about, I'm going to write this. One quick qualification too from here on in, and this is not, anyway, from here on in this branch of physics, classical mechanics, like when we're looking at the macroscopic nature of objects observably moving through space and time, mechanics, Newtonian physics, Galilean physics, in other words, physics 203, like, or in other words, as opposed to electricity or waves or something like that. When we're doing this kind of physics, anytime we talk about a mass, it doesn't matter whether it's a coffee cup or a whole planet or baseball or whatever. We pick a location, a dot, like a Euclidean dot. We pick a point at the center of that mass, and that's sort of a technical term, and sometimes that's not literally its geographic center, but we pick a point that represents the whole mass that's essentially at the center of it. And we act like, and this is what we're always going to do from here on in, like I'm going to forget to say it a lot of times, but even if I'm talking about the coffee cup and say, oh, the coffee cup is sliding down the table, or if you're doing a lab and you're talking about like some ball rolling down a slide or something, whenever we say ball or say coffee cup, what we're actually doing when we solve the problem is we're focusing our attention on one dot that in the center of that coffee cup, and we act as though all the mass, all of the kilograms of the coffee cup are all focused right at that dot. In other words, we don't want to get that bogged down right now in the details of shape or something. We don't want to get confused if like one part of the thing can move compared to another part of the thing. We just treat all, and this is not a student teacher thing. This is like a physics approach thing. In this realm of physics, whenever we're talking about a mass, we actually only visualize or analyze a point located at the center of that mass. We act as if all of the kilograms are like enormously densely concentrated right there. And from there on in, we treat the mass as what we call a point mass. Okay, so from now on so from here on in this way of thinking, there are points of mass located at points of space at various points in time. And these points of, like pixels, okay? That's how we treat things. And then, like anything else, like the more we understand that, then we add details and add shape and get more and more complex in our analysis. But a mass from here on in is a point mass, okay? And it's measured in kilograms. Now, F net equals ma says that Newton's second law tells us that whenever we have some point of mass at some point in time, at some point in space, if we were to know all the forces acting on that mass point, right then, we would know, right then and there, we would know the acceleration. We would be able to figure out the acceleration of that point mass right there and then. Like Newton's second law is a prediction. If you know how hard something's being pushed, you're going to know at what rate it's going to change its velocity. Um, um, so, sorry. So we need a method for figuring out all the forces acting on an object, and in what directions they're acting and stuff like that. And that method is called the free body diagrams. But just one thing before I go any further about units. Okay, just to be clear about units before I go any further, in the simplest terms, what F net equals ma is saying is like, if you want to take 1 kilogram object, okay, and that's like kind of like an apple, let's say. That's not exactly right. I mean, the apple isn't quite that heavy, but like a very heavy apple, or maybe a cantaloupe or something. That's probably too. But say a really big, heavy apple, like that's because a kilogram turns out to be about 2.2 pounds. So like a very heavy apple, if you're holding in your hand and you want to either speed up or slow down this apple or turn it, let's say speed up, you if you want to take the apple from rest up to a speed of like 1 meter per second, which is about 2.5 miles per hour, so like not that fast, but it's about how fast you walk, right? You want to get this apple up to a speed of 2.5 miles per hour in 1 second, right? You want in other words, if you want to give this 1 kilogram apple an acceleration rate of 1 meter per second squared, which means not a speed of 1 meter per second, but you want to get it up to a speed of 1 meter per second in 1 second, right? That amount, the amount of force, how hard you'd have to push it or pull it to do that, the amount of force required to accelerate 1 kilogram by an amount of 1 meter per second in 1 second of time, that would be 1 unit of force. And 1 kilogram times 1 meter per second squared is 1 unit of force. And we call that unit from now, not surprisingly from now on, a Newton. Okay, so the Newton is the unit of force. 1 Newton by definition equals 1 kilogram times 1 meter per second squared of acceleration. Okay, just to get that straight. So we're going to measure forces in Newtons from now on. That's what we're going to do. And that's different from kilograms. Kilograms are a unit of mass. Newtons are a unit of force. Okay. Oh, hi. Hello. Oh, okay. Sorry. What a free, so the law says if you want to compute if you ultimately want to predict accelerations, which is ultimately what we want to do. Put another way, the whole first chapter of this, or the whole first set of chapters of this course was all about analyzing accelerations of objects. And once you know the acceleration, you know their future velocity and you know how far they're going to get and all that, which is the whole point of physics. Well, it's like we're backtracking. Acceleration was the effect that we've been analyzing for like months. Now we're backtracking to the cause. Now we're saying, well, where does an object get acceleration in the first place? Where it gets like naturally, objects on their own don't accelerate. They accelerate if they're being pushed or pulled by other objects. They accelerate if they're being forced to accelerate. So now we get into so our mental picture now is like, as long as I know all the pushes or pulls happening to a particular object at a particular point in space, at a particular point in time, then and only then I'll be able to know what that object's acceleration is at that particular point in time, at that particular point in space. So the whole issue now becomes, well, how do we know what all the forces are acting on an object? Like, how do we know what they are and how do we know what they're doing? Like, which way they're pushing and how strong they are? The way we put that all together, or the way we figure all that out, is in this thing called a free body diagram. It's super important, super important. It's not just like a rough sketch of stuff. Like, I know we're very used to drawing sketches and pictures in science, but this isn't just like a picture. This is like a graph in that it is a calculational tool. Like these things are used to figure out stuff, not just to kind of loosely represent it. And in fact, you cannot do you really can't do a physics problem, particularly not a force problem, without beginning with a proper free body diagram. And the free body diagram, if it's set up properly, will show you what cranks to turn and what math to do and all of that. But for all of those of us who have ever said, I kind of get physics when he's doing it or when it's being talked about, but I never know how to start a problem. From here on in, this is how we're going to start problems. And this is to my point in life, but to this day, like if I have to sit down and start a physics problem that I don't know how to do, or I don't know what the answer is, and it's like a real problem, the thing I always start with is a free body diagram, and the free body diagram sets everything up and makes the math happen. Okay, so it's like a very real thing, and I certainly didn't make it up. So that's what I'm going to start. We're going to do free body diagrams here. I'm going to start with the simplest case, the free body diagram of the simplest case. In other words, I'm going to start with a free body diagram where only one force is acting and see how the diagram works, and then we're going to add forces to that. So sorry. Okay. Okay. So we're going to first look at our good old friend, common example of free fall. Let me remind you what we said about free fall like months ago. Free fall, it's a very important case to do first. First of all, because it's like common and familiar and relevant. It like comes up all the time. But also, it's in a way the simplest thing that could be happening. Free fall, because remember, a force is something that comes from another object. So if I picture the case of free fall, I'm picturing a case where I have a mass, like maybe it's my coffee cup, maybe it's a tennis ball, whatever, or maybe it's a brick. I have and by that again, I really mean the center of the coffee cup or the center of the tennis ball or the center of a brick or something. But I have some mass, some number of kilograms that I'm going to say is being affected by nothing, like by no other object. It's not being pushed or pulled by a table. It's not being pushed or pulled by my hand. It's not being pushed or pulled by like a gun chamber or anything. We have an object that seems to be, in fact, totally by itself, seems to be affected by nothing because it's being touched by nothing, but except for the one big object that actually always seems to be here with us and always seems to be affecting stuff, which is planet Earth, right? Like planet Earth is always there. And what we seem to know, I don't know why at this stage, but I know from experience that like anything I let go of, anything that I think I'm not touching at all, anything that seems to be by itself, always seems to be pulled toward the center of the Earth and fall down. Now, again, I don't necessarily, I mean, I do, but like we don't have to at this stage know why. Newton didn't know why. Aristotle certainly didn't know why. And we don't know the inner mathematical workings of it like yet. But what we just observationally as scientists know is things always seem to be pulled down towards like the center of our planet. And I say the center because, you know, if we were in Australia, like things don't fall up, they fall down. You know, everything seems to always be pulled toward the center of our planet. And we call that gravity, right? Again, I don't know what the inner workings are, but this just phenomenon, this fact that the Earth is always pulling things, seems to be a phenomenon. So free fall is when an object is being affected by nothing but that. But that is a force. So free fall is a case of one force acting on an object. Now, again, remember, if there's no forces acting on an object, then there's no diagram to draw. There's nothing. There's just Newton's first law, nothing to be worked out. So the simplest case of force is that is one force, and the force that we call gravity. So how do we diagram this? The way to diagram, that's always going to be true. So the rule that I'm telling you right now, this is the rules for how to draw a free body diagram in general. In general, whenever we're drawing a free body diagram, no matter how complicated, we put a dot in the center of the page to represent the point mass in question. And then for every force that's acting on that mass, we draw an arrow starting with its tail at the mass and then to a tip that is pointing in the direction of the force itself. Of course, I'm going to do that in one moment. It's an arrow, but specifically it's a vector arrow, meaning that it's going to be oriented in the particular direction that we intend. Like, in other words, direction, it does matter, and we are trying to keep track of it. But also, it's going to represent magnitude, at least approximately, in that the bigger the force is, or the bigger the force we believe to be, the longer the arrow will make. Okay, I mean, it can be approximate, but that's the idea. So now that's actually, in a way, the only two rules of drawing a free body diagram is just draw an arrow for every force acting on the object. But to see this play out, let's do it here in this case. In this case, there's only one force. Okay, this is, as usual, I'm spending a long time on the simple case to show you, like, because once you get really how to do the simple case, then you get how to do the complex cases, which is the point. So I'm almost done here with, so in the case of free fall, we have an object M here. The dot is representing the object M, and there's only one force acting on it. That force we call gravity. And that force is pulling the object down. So I've drawn an arrow pointing down. Please note, this does not mean necessarily that the object is velocitizing down right now. Like, remember some of the problems from the midterm, like the object, like, it's being affected only by gravity. So it might be on its way up before it comes down, or it might even be going to the side, like in lab 4. This arrow does not represent velocity. It does not represent motion. It represents how the object is being pulled. And if I thought it was a very, very heavy object, I might make it a longer arrow or whatever, but that's just the pull. Now there's one last thing I should say. Sorry, there's one more rule. So yeah, we draw a dot. For every force acting on the mass, we draw a vector. But then rule 3, the last thing we're going to do in any free body diagram, I mean, ultimately free body diagrams have lots of arrows in them. The last thing we do is we're going to label each arrow. Okay, and we're going to do that right here. But we're going to label the arrow with some kind of label that identifies what the force is, what type of force it is, or something about the force. But we don't usually put a number there. The purpose of all the arrows ultimately is to get a number. And we're using these arrows to figure out numbers, but we don't put number. I mean, this is a subtle point, but we don't put numbers in the diagram. Again, the diagram is meant to figure out numbers. We put identifiers in the arrows. So, like, right now, I could write, the only word we know for this pull right now is I could write the word gravity. I could. But before you write that, I mean, you could, and that wouldn't be incorrect, but a more common word for that we want to start knowing now, a more common word for that is weight. Weight, as you might remember from chemistry or something, is not the same as mass. It's related, but it is not the same thing. Weight is okay. I have to start being explicit now. So weight is a synonym for gravitational force. Okay, weight is not a synonym for mass. Weight is a synonym for force. I'm sorry, it is a synonym for gravitational force. Specifically in our context in classical mechanics, if we're doing stuff on Earth, if we're like looking at baseballs or trucks or balls on ramps on the surface of planet Earth, then we see everything on the surface of planet Earth is being pulled toward the center of Earth. Again, we don't necessarily know why yet. And I keep saying that because like Newton didn't, but he did all this physics anyway. So it's not, and so it may be like an item of curiosity, but it's not an obstacle. We don't quite know why gravity does what it does, but we see that it's happening all the time. We see that the Earth is pulling down everything. So that downward pull, and a pull is a force. The downward pull exerted by the center of Earth on any and every given mass that you ever think of, like not only is it always there, it seems, but it's so common and important, we give it a name, we call it weight. Okay. And technically, like if we all lived on Jupiter or whatever, then by weight we would mean the amount of gravitational pull that everything was experiencing from the center of Jupiter. Like, but we don't live, and those would be different numbers, we'll see, but we don't live on Jupiter, we live here. So when we say the weight of an object, we mean how hard it's being pulled down toward the center of the Earth. So to be even more specific, then so then that's the arrow that's in that diagram. To be more specific, then right? So just before I go any further, in the metric system, in the SI unit system that we're in here in science, the units of weight are newtons, because weight is a force. It specifically is the gravitational force, but any force, every force is measured in newtons in our system. So the weight of something is some number of newtons. It's how hard it's being pulled toward Earth. It's as opposed to mass, which is measured in kilograms. Okay. And let me also say, if you're wondering, like, where do pounds come into all this? Pounds are not part of the metric system, just to remind you. And again, I know that you all know all of this, but I'm just trying to package it together for physics purposes. So I'm not trying to insult anybody nor bore anybody, but also it's possible that you never did like put this together. So mass is measured in kilograms. Weight is measured in newtons. 1 Newton equals 1 kilogram times 1 meter per second squared of acceleration. Okay, so they really are different. You'll see there's relation, but pounds, ultimately what pounds are the non-metric equivalent of newtons. Pounds are a measurement of weight, yeah, but in the American or British or whatever stupid system that we're in. So pounds, and there's conversion units between all these, as you know, like 2.2 and this and that. But like, I'm not going to talk about pounds here because we're in the metric system. But if anybody ever says, like, if anybody ever says my weight is 150 pounds, yeah, they're telling, like, mine is basically, I'm telling the truth. My weight is about 150 pounds. But what that means is the earth is pulling me down with a force that is 150 pounds, which is equivalent to some number of newtons. That's not my mass, that's my weight. Newtons are equivalent to pounds. Kilograms are equivalent to something that that you never ever hear of and you never use in America, but they're called slugs. Like, just for the record, like, if you're trying to complete the analogy in your mind, okay, you never measure mass in the American system commonly, which is what makes the whole thing so confusing. But whenever people talk about pounds, they're actually talking about units of force. They're talking about the units, the amount of force that the earth pulls down with. Okay, so what I want to figure out is, like, wait, sorry. I'm still in the topic of the free body diagram here, but I'm writing a question. This is not, you can, oh, there's something in the chat. Oh, that's awesome. I will look in 1 second. Sorry. And maybe it's, I have to leave right now. Yeah, Yaverbaum, please forgive me, in which case that's fine. I probably already missed, they probably already did leave, but hold on a second. Oh, I knew it. Okay, cool. Yes, no problem. If oh, right, okay. How did I know that's what the question was? Because I heard the sound. All right. Because I know I'm being so boring that there couldn't possibly be any questions right now. Okay, so but I just asked a question here in blue, but it actually is a rhetorical question, even though I would love the participation, but I also know we're running out of time. So it's a rhetorical question, and it's so we can finish this free body diagram intro. Now, again, I'm spending a lot of time on a free body diagram that has 1 freaking arrow in it, but this is the way of physics. If you really understand how to draw 1 arrow, then any diagram that has 3 arrows, you're just going to do this procedure 3 times. So if I'm wondering, okay, wait, so let's say I have a mass of 1 kilogram. Well, and Yaverbaum is saying, okay, that's its mass, but its weight is something else. Its weight is how hard it's being pulled to the earth. Like, well, okay. And Yaverbaum is saying, that's me. Yaverbaum is saying, well, the number of kilograms it has is not the same, like, that's not the same thing as its weight, and weight is measured in newtons. So it's very reasonable to ask, okay, if something has 1 kilogram of mass, does that mean it has 1 Newton of weight, or like how much weight does it have? Well, to find out, let's look at the free body diagram and look at the situation. Like, even though this is a shockingly simple, almost dumb looking picture, it's just 1 arrow, it's actually, even just this 1 arrow is going to tell us something. Like, if the free body diagram for free fall, we just said looks like this, right? And right now I'm saying that this arrow could be labeled weight, like, right? Well, here's what we do with this free body diagram. Here's the whole point. We have this 1 diagram, 1 arrow with 1 force, and whatever that force is, like, it's measured in newtons. I'm now confident. I look at my diagram and I'm like, okay, the diagram is showing me all the forces that are acting on an object. It's showing me all the forces that are acting on the object in every axis, in every direction. Happens to be only one. Now that I'm confident that I have all the forces drawn, the purpose of it is I can now, the reason for the diagram is to apply Newton's second law. Now, Newton's second law says, if you look at any particular axis, add up all the forces acting in that axis and subtract all the forces acting in the opposite direction in that axis. And that will give you the acceleration of the mass in that axis. Okay, right? So the left side says add up all the forces. And this is why we have to draw a diagram to see what to add up. Well, in our diagram here, in this like dumb, simple case, there's only one force to add up. Okay, so I'm gonna, and it's pulling down. So I write it down. Weight, that's the sum of all the forces. There's only one. Well, according to the law, weight will equal the mass of the object times acceleration. Okay, now we're in free fall here. Like according to this picture and according to Newton's second law, the force acting on this object M will produce the acceleration of the object A. We're in free fall here. We know the acceleration of any object in free fall. Like, and this goes back to the first, to the midterm. Like, even if the object happens to be moving up right now or moving to the side or whatever, we know that its acceleration is downward pointing a number of meters per second, a constant, which is approximately 9.81 meters per second squared, or approximately 10 meters per second squared, pointing down. You can call it negative, but negative just means down, and there's only one direction here, so I don't even have to, like, I'm just going to call everything that's going in that direction plus. I'm not even worried about the negative sign. And I could quibble over whether that thing is 9.8 or 10, but actually none of that matters. What we were doing on the first exam, and we're going to continue to do here, is say that constant. Well, here, we're going to remind ourselves, and I know there's 5 minutes left, which is perfect. We're just going to finish this problem and we'll be done in time. Like for free fall, we know by definition that A is a constant, and that constant is what we call lowercase g, right? Lowercase g generally stands for 9.8 if you're trying to be sort of exact, like in the lab, or 10 if you're being approximate on a test. Or by the way, it might even be a different value if you were on the moon or on Jupiter, but we just call it G. We call it G to stand for that constant acceleration under free fall, right? So that means, next page, and we're almost done. That means according to this picture, according to Newton's second law, we can say that the weight of an object equals its mass times its acceleration g. That is the now here's the and almost done. 1 page left, 3 minutes left. What I want to make clear here, and again, I know that you might have already known these numbers or whatever, but I'm trying to get this straight so that all of our free body diagrams for the future are okay. Well, the first fact that I'm saying is if you have a mass of 1 kilogram, then you have a weight of like 9.8 newtons. I mean, that's the concrete thing I'm trying to say. The conversion factor is 9.8, not coincidentally, because 9.8 is the rate at which things accelerate to the ground during free fall. Now, I want to make this a step clear. So first of all, if your mass is 1 kilogram, then your weight is 9.8 newtons. If your mass is 2 kilograms, then your weight is 19.6 newtons. Your weight is your m times the number g. That's the first thing I'm trying to say, and that you can take to the bank. Like that's a memorizer. And someone say, okay, that's the other class. That's always true. That weight. I mean, in other words, the big takeaway really here is that your weight equals mass times g equals your number of kilograms times the free fall acceleration rate in meters per second squared. And so your weight is in newtons. But the other thing, okay, but the other super important thing I'm saying now is we just use the case of free fall to figure this out. And we use Newton's second law to figure this out. Like in free fall, by definition, there's no other forces acting on you besides your weight. And we know that in free fall, you accelerate at 9.8. Therefore, we figured out what your weight is based on that 9.8. But this remains a true fact whether or not an object is in free fall. That is to say, objects always have weight. The Earth is always pulling on them, whether or not other things are happening. So even if an object is on a table, it still has weight. It's just that other things are now happening to balance out that weight, like the table is pushing up. So the big thing that I want to say, the big takeaway here, as far as drawing free body diagrams are concerned, and you'll get into this with Wu as well, but from here on in, so this is the last thing I'm writing. I know we have like 1 minute. We have to, this is the last. Okay, this is the super important. This is the last thing I'm saying, but please get it. I'm saying from now on, free body diagrams will have a lot of arrows in them. For every other force that's acting on an object, there'll be another arrow. We have to get into that. But here's the deal. All objects have weight. So every time we go to draw a free body diagram, the first thing we do is we draw that downward arrow because it's there no matter what. And we're from now on always going to label that arrow mg. The weight of an object from now on is always mg. mg is always in every single free body diagram. It's the first arrow we draw. It's always there. And then every other arrow we draw will be every other force that's acting. And how do you know what other forces are acting? It's super simple, so simple that people get it wrong all the time. Besides gravity, the way to know whether there's a force or 15 forces or 27 forces is look for touches. Any other thing that's touching the object makes a force. Like for every other force you think might be there, ask yourself, is there anything else touching this object? If a string is touching the object, then the string is exerting a force. If your hand is touching the object, then your hand is exerting a force. If the table is underneath the object, then the table is exerting a force. From now on, all forces are touches and all touches are forces, with the one grand ever-present exception of gravity, which is the other reason we always draw it first. Gravity is always there and it doesn't involve a touch. It's mysterious that way. So mg is in every single diagram, but then past mg, you draw arrow, one arrow for every touch, and for every touch visualize you draw one arrow. That's all I got today. Sorry, that was 3 minutes over. I'm so sorry. I'm just gonna say goodbye, and the other class is coming in. So I hope that was clear. Goodbye. I'll see you, and I'll have you. Thank you very much.
Thank you, Professor.
Thank you, and I'll get your test back. I really will. Thank you so much for being so polite. Okay, bye. Thank you, and I'll post everything.